All right. My name is Avik. I work at Facebook. I joined Facebook around 4 years back and started this Flow project around that time. So I'm going to talk about basically what Flow is about and discuss some of the things we are thinking about um, uh, in regards to how to improve Flow in the future. Before I start the talk, because this came up in the previous talk, I did check in my head that the first few examples, at least, I think Flow would catch those errors. And the last example, as Brian said, that would also be caught by Flow. Exhaustiveness is like a pain point for us, as was pointed out. But we're also considering some solutions there, and whether we can enable stricter checks in certain modes and so on. So I'll come to some of that later. All right, so um, at Facebook, we used to have this saying, move fast and break things, which was something that was very core to a very core value that we had. At the time, this worked great because if we did not move fast um, and necessarily break things as a compromise in order to move fast, we would probably be irrelevant at this point. But as the company grew, we realized that moving fast is okay, breaking things is not so okay. So at some point, we changed our values to be like move fast with stable infra. This kind of doesn't sound as good, but that's what it is right now. All right, so why am I saying this? Well, Flow is a static type checker for JavaScript, and was built around this time when we were slowly transitioning into a kind of a large company which hires lots of engineers, and they all have kind of banging on the same code base. Um, they're breaking each other's code all the time. Meanwhile, code is becoming kind of really large. Lots of engineers being hired, and all of them are writing tons of devs every day. So can we kind of bring some sanity to this picture? And it turns out that yes, types are basically a tool to do exactly that. They're kind of a very modular way of reasoning about your code. And JavaScript actually is a nice language that way, in that you actually break up your code into a lot of modules, which are by themselves really small. So you can reason with types at the boundaries and ensure that one of these engineers does not break some other engineer's code, or they know exactly what arguments to pass in when to a function that somebody else wrote. If they want to refactor something, that they know that the type checker has their back. Right. So those were the kind of the lofty goals that Flow was started with. Um, so we do development inside Facebook, where we kind of push every diff out to GitHub. So that's where like the external focus is. I would like to highlight that this is used at Facebook quite a bit, but it's also based on pretty solid theory. So we just published a research paper on the internals of Flow. Is going to appear at UPSLA, which is a programming languages conference, pretty soon. And we're going to present that paper next week. So I have a kind of a theory background. I have a PhD in type theory. I did not know how to code. I landed at Facebook and started building this tool. So then I learned a lot of engineering, and kind of both of those worlds kind of make their presence inside Flow. So let me go quickly over some of the design goals that we set out to achieve at the outset. These are not necessarily design goals that every type checker for JavaScript embraces. They may not be the right design goals for every tool that you build, but these set of tools were especially very critical for a use at Facebook. So one is precision. And by precision, we mean understanding the code as it is written. And this is very important for us because we have a ton of code written at Facebook, which is basically JavaScript. And we do not want to layer on a kind of a different language onto that JavaScript. We really want to follow along kind of the source of truth, so to speak, and model what's going on at the level of types. So if you look at this picture, what I'm trying to show you is that there is kind of a continuum where a static analysis tool can basically come in and say, okay, I'm looking at this code, and at the extreme on the left, you have basically the type checker gives up every time and says, well, this code, I will not accept this code. And that's very easy, but that's not very usable. On the other side, the type checker can be basically just say that yes, anything goes. So it will not be able to catch runtime errors of the kind Brian was talking about in the Elm talk, and that's pretty bad as well. So we made this conscious choice that there's this barrier in the middle, which is called so-called soundness barrier, if you will, which basically says that the type system has to be sound, and that was one of our design goals from the outset. What that means is essentially what Brian was referring to is that if the type checker passes your code, then you will not have any runtime exceptions. Now, not all runtime exceptions, but I would say type exceptions. If you divide a number by 0 in most languages, you do have a runtime exception, but that's not the kind of thing that you can catch easily through static analysis. On the other hand, a lot of common errors like accessing a property that does not exist or adding a number and a string and so on, those are very easy to catch by a type system. So we had this basic goal, and it's surprising that, again, a lot of type checkers for JavaScript do not necessarily conform to this kind of soundness requirement, but we did have that from the outset. I will add a lot of caveats to this claim. JavaScript is a hard language. I do not claim that we are sound, but we are aspiring towards soundness, and that's also something. And there's a story around what to do about the unsound parts. So the other thing I want to highlight is that there's a curve here. The green part is where you're kind of slowly moving from a point where you're giving up all the time to actually trying to accept exactly the set of programs that do not fail at runtime. And the limit is impossible to achieve because of the halting problem. This is like a fundamental block in computer science. So all you can do through static analysis is aspire to get to that limit, right? And there is a point in which you get diminishing returns given the language that you're working with. There's a point where you can be more and more precise at the cost of maybe resources or more work from the users or whatever. But at some point, it does not matter anymore. For most programs, you've kind of reached a plateau. So there's a notion of optimal precision. So when I say that flow is precise, I mean it's precise enough, right? So there's no sense in which it is fully precise, because then I'd be lying. So if you want like slogans, it's on the left. You want to reduce noise, right? If you are erroring all the time without really understanding the patterns of the language, then you're basically introducing a bunch of noise, and the user is going to just ignore all of those errors and code in whatever style they want anyway. And on the other side, like soundness is such a big requirement because in the end, you want to encourage a programming style where you're trusting your types. So you do not want to add types to your code and then also have runtime checks, dynamic checks, type of checks, instance of checks, and so on, as like a final fallback, because all you did through your types was just maybe get some autocomplete and whatever else, but nothing much more than that. So we don't want that. We actually want types to guarantee some sort of like trusted interfaces. All right, so the other design goal is speed. JavaScript is successful for a reason. People actually iterate pretty fast when they're coding in JavaScript. And the only big problem with JavaScript is it doesn't scale when you have lots of people working together, right? So we want to solve the latter problem, but not at the cost of like completely, changing the character of the language. In particular, we do not want to slow the developer down too much by introducing the so-called compile time step, right? So we have C++ programmers at Facebook, we have JavaScript programmers at Facebook. C++ programmers are pretty unhappy with the compile times. We don't want to aggravate JavaScript developers with that pain, right? So there are lots of things that we do engineering-wise to make flow really fast, even for huge code bases. So talking about tens of millions of lines of code, we have monorepos we have two mono repositories, which is kind of a weird way of putting things, but each of these repositories is pretty huge, running into tens of millions of lines of code, more than 100,000 files. So this is like, really big code bases. So we do all of the things that you might imagine we need to do, which is, one is work in the background, utilize idle time, kind of start our work as soon as things in the file system change, and not really wait for the user to kind of say, okay, now I want type errors, so start the work now. We parallelize as much as possible. We usually develop on dev servers that have lots of CPU and memory, so we kind of try to use as much resources as there is in the machine. We also try to minimize work as much as possible, which means we have a very good incremental type checking story. So we try to reuse as much work as you can, so that when you change or do a trivial edit on a file in a large code base, we don't have to compile everything, right? So we kind of try to compile only the things that are necessary or invalidated by your updates. And again, going back to the graph, I was talking about optimal precision. This is one of the things that directs that optimality, right? So things get progressively harder the more stricter your type check, the more precise your type checker is, right? So if you try to understand more and more patterns, there's some sort of like limit to that, beyond which things get really expensive. So there's kind of a very delicate balancing act on exactly what the type system should look like. All right, so enough talk. Let's look at some examples just to give you a flavor of what kind of JavaScript we type check using Flow. So there's a simple function that looks like it just computes the length of something by looking up its length property, and you call it with a string, and things are okay, because strings have a length property. You call it with an array, and things are also fine. So this is already going beyond some languages like ML or Haskell, probably Elm also, because it's based on Haskell. In that, if you say that the type of X is determined by any one of these calls, then you would have to reject the other call, right? So that this is one of the fundamental design choices that Flow had to make in the language of types, which is it needs to be comfortable reasoning with sets of disparate sets of values, not just one kind of value. So until this point, Flow actually thinks that this is fine. And now it complains. You're trying to call length with the null value, and you get some redlining saying that this is going to blow up at random. So it's instructive to see what actually happens at runtime to figure out what Flow would do, because as I said in the beginning, Flow is just trying to model what happens at runtime, right? So there's going to be a null value, and you have a function call, so it's going to reach the parameter of that function and get bound to it. And from there, it's going to reach the property get. And at this point, you're going to get, length not found or null or whatever. So one way to think about Flow is that all Flow does is run this code statically. So if you actually use an editor with Flow and you hover over X, you can see the type of X that was inferred by Flow at that point, which is actually a union of string and null and this kind of tuple type, if you will. It's kind of it's trying to be as precise as possible. So it could have inferred that 1 to 3 is just an array of numbers, but it knows more than that at this point. If at some point it doesn't need this extra information, it can always throw it away. But at this point, it has that knowledge. And in particular, it knows that null is one of the possible values that can reach that property get, and that's why it's in it. The way it figures this out is that it assigns types to everything that it can see, all the expressions in your code. So null gets a type null, which basically just describes that null value, nothing else. The parameter X, which does not come with a type annotation, gets some type capital X, which is an unknown type. And the type of length can be described in terms of these things, right? So length is a function that that takes an X, a capital X, and returns some type that is elided for the moment. So we won't bother with that right now because it's not relevant for this example. So when it looks at any expression in your code, it tries to generate so-called constraints that kind of dictate what the type of the involved expression should be like. So if you have x dot length, then then M is this constraint that is shown in yellow, which says that x flows to this use, which is a get prop of this length property, and it returns this get prop should return something that's elided in that box. Similarly, you have a call of the length function. The length variable has a type, which is function type, and it is being called. So we emit another constraint that says this function flows to a call, and the call has a null argument. And again, the call returns something of a different type that is elided. So basically, then we can simplify this so-called call constraint. And the intuition here, there's a typing rule for it. But a lot of type theorists kind of use very fancy words to explain what's going on. All that is going on is that you're simulating what happens at runtime, right? And at runtime, what happens is when a function gets called, the argument goes in the opposite direction and actually flows to the parameter, and the return of the function flows to the result, right? So there are two different directions of flow, and type theorists like to call this contravariance and covariance, and they use all sorts of fancy features, and then users get scared, and then other type checkers basically say that, okay, users are never going to get variance, and therefore they introduce unsound rules in their type system. They don't need to. All they need to do is explain that this is just a function call. This is just simulating what happens at runtime. And at runtime, what happens is null goes to X. And then now, just like values flow through variables in your code, so do these types through these constraints. So if you have null flowing to X and X flowing to something, then you have null flowing to this get prop instruction. And at that point, you can say that there's an error. Why? Because null, you're basically doing a get prop of length on null, right? So that's the interpretation at the type level. If you want to fix this code, it's pretty easy. This is what most people would do. You would check for null, return something that's a number, and like move on, right? And then Flow is happy with this code because at this point, what it's trying to do is, okay, let's look at what happens at runtime. If you do pass in null, then that null value is unreachable at the x.length expression right now. So this is effectively what Flow would infer as well. It would say that in the if branch, x can branch in two different ways. So it will be refined, so to speak, with these two conditions, double equal to null and not equal to null. And the value that can pass through these filters will be captured by x1 or x2, right? So x1 where x where x is equal to null will go to x1, and x where x is not equal to null will go to x2. And it's the x2 value that, so the else branch of the if, which will actually have the get prop, which will flow to the get prop instruction. So if you plumb all of this through, null is equal to null, so that part will just go through. So null will flow to x1. However, because null is not equal to not equal to null, nothing will flow to x2. So at this point in this graph, you do not have a reachable path from null to that get prop instructions. This is why there is no error in this example. Right? All right, so just generalizing this code a little bit more. Don't worry about the specifics of this code. This is just a stupid function that I wrote to print items, and it's taking array-like things like strings and arrays, iterating through all of the elements and printing them out, right? So that's, this is not real world code, but this is the kind of code that if you wrote, Flow would again redline this code. Can anybody say why that might be? Good. This is the type checkers. Oh, you are faster than a type checker. Ooh, Yes. So you've probably caught a bug that is outside the scope of the type checker. If you look closely at the call at the bottom, line 17, it's passing this weird object that has a length property, but the length property is a string, and you're trying to kind of on line 11, you're getting the length of y, and then you're comparing it with some number, and Flow is upset with that. So you can confirm this by hovering over len, and you will see that it's either a number or a string. And it figured out it was a string from that call on line 17. So there's a lot of type inference going on here. All right, so let's pick up the action from where we left it off in the previous example. You have this kind of setup where one of the branches of x goes to x2, and x2 goes to this getProp instruction. You also invent a type variable, like an unknown type for the parameter of print items. Looking at the call of length of y, you know that y is flowing to x, which is the parameter of length. In a very similar way, you know that print items, which is also a function whose parameter was y, it's getting an argument whose type is length colon string. So it has an object type that has length whose type is string, right? So that's flowing to y. So now you start joining things, and you have this object type flowing to x, and from there it flows to this, refinement constraint. An object type is not null, so that's fine. It just goes to x2, and from there it goes to this instruction. And until this point, actually things are fine. You're passing an object type to where you have a getProp instruction. The property exists on this object. So this is actually going to pass until this point. So now we need to introduce something else. So remember the result of the getProp that we were eliding until this point. Let's say that the result is R2, and R2 flows to the return of length, which says R. So we just blindly emit constraints, just looking at how things flow through the program. Meanwhile, length is being called on line 11, and you're binding it to this variable len, which is being used as a number. So that's what R going to number means. And now you start joining things again, and eventually you get this constraint that string is being used as a number, and that's an error, right? So you cannot get around it. If there is a way, if there is a possible path through your program that will give you a type error, then Flow will catch it, right? So modulo whatever bugs it might have or other things, but not because of silly design choice. All right, so this is bad, and until this point, note that we have not added any annotations, but this does not kind of really scale. At some point, you have to pin down the API, and that's what types are good for. So I want to stress this point. The typical mode of things is you don't necessarily have to write types everywhere. It's kind of an accepted style if you do want to program that way, but you can get a lot of mileage even without types. And then at the boundaries of your modules, that's where types become really helpful. So for example, if you just typed the parameter of print items with the proper type, like the string or array of string, then you can actually get rid of the null check in length, because you know that length is a private function, and you're not calling it with the null value. But note that now you're trusting that this type actually captures only strings and arrays of strings and not anything else. If you're importing this function from a different file, you can get this type through tooltips. And at this point, if you try to pass in null, then the type checker is going to yell. So the blame has been shifted to downstream to callers of your function, rather than you having to code in a very defensive state. This is one of the advantages of using types. So this kind of changes how you code from a very defensive style to kind of relying more on types to give you invariance. This is just a small flavor of the kind of feature that Flow has. There are lots more going on. None of this is like really unnecessary. All of these try to capture real patterns in JavaScript that we see every day, at least inside Facebook and also outside Facebook. In particular, you might see disjoint types, disjoint unions thing that in the previous talk, you saw those weird unions with values. That's actually a very common pattern in JavaScript, especially for Flux-like code where you're dispatching on various kinds of actions, and you want to distinguish which kind of action you have, and you have some associated values with each action. You can capture all of that using the so-called disjoint unions, which map extremely well to Haskell or ML or Elm data types. Literally lots more going on that I'm not going to go into today. All right, so zooming out, let me share a small anecdote. So you mentioned this paper that we were writing on Flow, and we started last year, and we submitted to one conference and it got rejected. But then we submitted to another conference after that, right? And I did a bunch of measurements when we were doing this, submitting that paper for the first time. Every nice paper should have an experimental evaluation section with lots of experiments and results and so on. So I did this, and if you look at the crosses, basically on the horizontal axis there's time, and on the vertical axis there's number of files in this one of our repositories, right? Which again goes into tens of millions of lines of code. Last year, I measured the total number of JavaScript files versus the number of files that were covered by Flow, and it was around 38%. This year, the same number is 86%, which means that year over year, like in the past year or so, the number of files, the total number of files has grown by 1.5x, and the number of files that are covered by Flow has more than doubled in the meantime. So kind of basically what's going on is that all new code is being type checked by Flow, and there are some bunch of laggards that are not typed yet. However, this does mark like a phase shift, right? So this is like, we were covering less than half the code, and now you're covering almost the entire code base. So it has a lot of implications that we can like ponder. Just to complete this, if you draw this graph, so October 2013 is when we started this project, and at that point there was not a lot of JavaScript. There was still quite a bit of JavaScript, not nowhere close to what we have now, and we had no covered files, and these graphs are like exponentially increasing. So we put in a lot of engineering effort in just trying to scale this analysis. And I'm not going to go into any of the engineering kind of decisions we took there. There are previous talks that I've given that are available on YouTube that you feel free to go check that out. But this is kind of scary. So the thing that I want to kind of drive home here is that even scaling linearly is not enough, right? So then what we did in response to this is something called lazy mode, which is incrementalism, like pushed to the kind of extreme, where given a code base, because we are kind of trying to type check every diff that people send out, we can assume that the master branch is always free of flow errors. And therefore, every diff that people send out, they might touch only a few files in the code base. We would only ever type check those and their dependencies and dependence and so on. Only the kind of the world in which an individual developer lives in. So this helps scale the analysis not to the size of the repository, but the size of the working set of an individual developer, which is more constant-like and does not scale linearly with the code base. By the way, this is just one repository. The other repository that I have has around half the number of files. The bigger one is for our website. The smaller one is for our mobile. The other question you might ask at this point is, what's coverage anyway? Like I gave you some numbers, 38%, 86%. What does that even mean? We are doing a very kind of naive counting of just the number of files that have this @flow pragma on top, which basically enables type checking for that file. Which means that any file that is not covered by that pragma is still untyped. So what happens at the boundaries? So when you're interacting, typed code is interacting with untyped code, what's going on there? So this is a real problem as we are approaching fully typed kind of code base, people want more and more, right? So they're already happy that we are catching a number of bugs that could cost the company a lot of money. Now they want to basically get to a point where there cannot be any crash of the website, let's say, because of a missed flow error. And most of the missed flow errors, recall, are from areas like this, not because of design choices that we make, but mostly through the interactions of typed and untyped code. So here's an example where you have an untyped code, but you're kind of, sorry, the green one is your file, but you're depending on a file that is not covered by flow. And you're importing something from that file. You don't know what its type is. You can basically assert that its type is anything, right? You basically then start building this tower of fantasy where you can say that, okay, this type that I just imported is an array of an object whose X property is number or something. And there's nobody who's checking that because on the other side, there's no coverage. We have no information. So people do that. And then, if you have adequate test coverage, then you probably are confident that the type you wrote down is okay. And then you can build more typed code based on that. But ultimately, your fundamental assumption there is kind of unvalidated. So this, you can consider this as some sort of like tainted input, where you are taking an input from an untyped file into a typed file. You can mark, even though you kind of cooked up some type for that import, you can still taint it by saying that, well, something untrusted is coming in into my code base. There's another problem in the opposite direction. If you export something to an untyped file, what can go wrong? Well, if you export a number, nothing can go wrong, because who cares what the number is being used as in the untyped code. But if you export something like a function or an object that is that the caller or the dependent can actually write back into, that is a problem. So you can have a public output, but if the public output has any writable parts, if we consider a function, the writable part is the input, right? So you pass in arguments. For an object, it's like any mutable property is a writable location. So if the untrusted code can write back, then that's like a tainted input flow back into your typed code. So the problem appears in both directions, and that's great, because this is exactly the kinds of things that types are good at. So this should sound very familiar to kind of the function and call rule that I showed, where I was talking about variants and all these fancy terms. If you just think of them as what's happening at runtime, which directions values can flow into, it's easy to see that, anytime you have a flow of a value from untrusted code into trusted code, you have a problem. You cannot trust your types. So the good news is all of this is amenable to type analysis as well. We just need to add some more information to our types to track these things, and this is actually something that we're working on now, which is called trusted types. This is, again, a lot of people in academia are doing research on similar things where they want to do efficient implementations of gradual type languages. We are very much in that bracket, and also trying to do cool stuff there. We also have, like, this is the ideal point where we want to go to, but there are other easier things we are doing in the meantime. I told you about this so-called strict mode that we are kind of exploring, where you can, flow does not try to be very opinionated by default. It basically waits for something to about to go wrong in your program before it really complains. But you can imagine that sometimes people want stricter type checks which have nothing to do with runtime errors, for example, exhaustiveness or some other aspects which do not directly map to runtime errors right there, but you still want flow to be more opinionated. Maybe you want flow to use flow for refactoring your code, and you would like stronger guarantees than no runtime failure. So you can implement them using a bunch of lint rules, and then we can hook it up with the so-called strict mode. So all you need to do is add, say flow strict instead of flow, and these configurable set of lint rules might fire. So we're exploring all of that, but this is where I spend most of my time thinking about nowadays. and also all the other opportunities that this uncovers, because once you have a fully typed code base and you can trust the types, you can do so much more. You can also probably drive transformations of your JavaScript, probably optimize them and so on. So there's a lot of exciting kind of stuff waiting to be mined from all of this progress. Well, leave you with this thought. Flow is marketed as a static type checker for JavaScript. We do not call ourselves like a language, but it's important to note that it's not just a type checker. It's just a static analysis that tries to do much more than just vanilla types.